This course is heavily focused on various lean tools and techniques. However, before we start deep diving through tools, let's answer some basic questions like what is lean and what are the key components of an effective lean transformation? So let's begin by answering the basic question, what is lean? Although lean can be characterized in many different ways, at this time I'll describe it in this way. Lean is the relentless pursuit of increasing value to customers through eliminating all non-value related wastes. The lean objective is to efficiently produce what the customer wants when they want it at the quantity and quality level they expect. As processes and work areas improve, there are many objective key measures or performance metrics that might be favorably impacted. The main three are lead time, efficiency, and material flow. Most, if not all, other submeasures drive one or more of these three. An effective lean transformation requires more than simply a collection of lean principles, philosophies, and tools. In this section, we'll be introduced to some of the critical components of a lean transformation. You may have seen this image before. It's the Toyota Production System house. It's a recommended and proven structure that leads to an effective lean transformation. As we begin to study this structured approach, let me draw your attention to the foundation. A solid foundation is a critical part of any house. And the foundation of an effective lean transformation includes three key ingredients. They are production leveling, standardized work, and a focus on developing a culture that encourages change. We'll now take a deeper look into each of them. Production leveling is a lean activity designed to minimize the production schedule variation or unevenness. Excessive variation or unevenness in the production schedule affects your ability to maintain the correct levels of material, equipment, and human resources. Now, during slow periods, you'll likely have more resources than is needed, which is inefficient and can be very costly. During high volume periods, you'll likely have less resources than is needed, which can impact lead times and the ability to deliver on time. The more we can reduce production schedule unevenness, the easier it is to manage the correct levels of material, equipment, and human resources. Another key ingredient to a solid foundation and an effective lean transformation is standardized work. Standardized work becomes a starting point for continuous improvement. Implementing standardized work results in a workplace that is safe, clutter-free, and well organized, and also highly visible. The example shown here is not well organized. For a manager or supervisor, it would be very difficult to know whether the work area is meeting its objectives. This example is much better and well organized. There's a place for everything and everything is in its place. A manager or supervisor can easily see if the work area is meeting its objectives because the performance is highly visible. Once both production leveling and work standardization has been implemented, it's time to begin creating a culture that relentlessly improves upon the standard. Once the foundation has been laid, we can build upon the culture of continuous improvement. There are two pillars of the TPS house, just-in-time and built-in quality. The built-in quality pillar of an effective lean transformation focuses on eliminating, alerting, and resolving quality defects. This is accomplished through mistake-proofing processes, implementing visual alerts to exploit problems, and a simple concept called Go and See. Go and See is a disciplined problem-solving philosophy that encourages rolling up the sleeves and going out to the place where the work is being performed to see firsthand what exactly is happening. These are some examples of mistake-proofing. When a quality defect is observed and understood, we want to go back and attempt to find mistake-proofing ways to prevent the defect from reoccurring. Poka-yoke is a Japanese term that means mistake-proof. When the potential for a failure cannot be totally eliminated, we want to at least detect and communicate the problem before it reaches downstream processes or external customers. Visual alerts can be very effective in getting the attention of the necessary resources. Some visual alerts can even automatically shut down the process if a failure is detected. To be clear, we don't want problems. However, if problems exist, we do want them to be visual so we can resolve problems in real time when they occur. The longer a problem goes undetected, the more difficult it is to determine the root cause and the more expensive corrective action can be. As mentioned earlier, Go and See is a disciplined problem-solving philosophy that encourages rolling up your sleeves and going to the place where the work is being performed to see firsthand what exactly is happening. Everyone has opinions and hypotheses, however, we want to objectively verify all assumptions rather than subjectively making unproven conclusions. Let's now introduce the continuous improvement pillar called Just-in-Time. The Just-in-Time pillar of an effective lean transformation focuses on establishing the takt time, creating a pull system, and eliminating waste. We'll be exploring takt time in a few minutes. However, as an introduction, takt time is the pace or rhythm needed to keep up with customer demand. In other words, the process needs to produce one product or service at this pace or quicker in order to keep up with customer demand. We'll also be discussing pull systems today in great detail. For now, let's just say a pull system is designed to efficiently produce only what the customer wants and only when they want it. Any activity that does not add value towards producing what the customer wants when they want it is waste or muda. Muda can be broken into these 8 distinct types or categories. In summary, as a result of laying a solid foundation and creating a culture that relentlessly continues to improve both just-in-time flow and built-in quality, the employees will have a much higher purpose and enthusiasm in the company. Your customers will also be excited to receive products and services with better quality, faster delivery, and the lowest possible cost. It's time for specific lean philosophies, methods, and tools. Now keep in mind, these tools are just tools unless properly coupled with a solid foundation or culture made up of scientific thinking men and women. Well, let's start by defining one of the most critical measures used in lean. This measure is called takt time. Takt time is the pace or rhythm needed to keep up with the customer's demand. In other words, the process needs to produce one product or service at this pace or quicker in order to keep up with customer demand. Another critical measure is cycle time. Now, cycle time is the actual time a process takes to complete an entire process cycle. Said differently, cycle time is the actual time a process takes to complete all of its process steps. Cycle time must be equal to or less than takt time in order to keep up with customer demand. An effective lean transformation relentlessly focuses on Mura, Muri, and Muda. Mura is a Japanese word that means work unevenness, while Muri is a Japanese word that means process overburdening. Both Mura and Muri are system-level factors and must be resolved first by management. The workforce can then eliminate process-related muda. Muda is a Japanese word that means waste or activities that add no value related to creating the product or service the customer needs. As mentioned earlier, the lean objective is to efficiently produce what the customer needs when it is needed at the quantity and quality level needed. Any activity that takes away from this is waste or muda. Muda can be broken into these 8 distinct types or categories. Defects occur when we fail to meet the customer's expectation. Overproduction is producing more than is currently needed. Now, overproduction is arguably the worst waste of all because overproduction causes many of the other wastes to occur. Now, waiting is any time spent waiting for any reason. Unused talent is where people's capabilities, minds, and talents are not being fully utilized. And transportation is defined as any time and energy spent moving material. Inventory is any material, raw, in process, and or finished goods not currently needed. Motion. Motion is the time and energy spent making unnecessary human motion. And finally, extra processing is defined as time spent providing a quality level higher than required by the customer. Eliminating these wastes is at the core of any lean transformation. All activities performed in a work area are either value-add or non-value-add activities. Value-added activities are activities that add to the form, fit, and or function of the product or service being provided. Customers are willing to pay for these activities. Conversely, non-value-added activities are activities that do not add to the form, fit, and or function of the product or service being provided. They are activities the customer is not willing to pay for. Much can be learned by simply observing a process. Standing in a circle is an exercise where the process observer literally stands in a 3-foot round circle for 30 minutes. They note all the non-value-added activity or mood observed. Once it has been observed, action can be then taken to eliminate it. Operator efficiency is the percent of total cycle time made up of value-added activity. It can be calculated by dividing the operator value add time by the total operator cycle time. As an example, if the total operator cycle time is 100 seconds and the value added portion of the total cycle time is 65 seconds, the operator efficiency is 65%. 65 divided by 100 equals 65%. Poor operator efficiency drives up cycle time, which results in a higher than necessary labor cost and a lower than necessary productivity. Minimum crew size is a calculation that determines the minimum number of operators needed in order to keep up with demand. It can be calculated by dividing the total cycle time by the total takt time. As an example, if the total cycle time is 354 seconds and the takt time is 130 seconds, the process will need a crew comprised of 2.72 operators in order to keep up with demand. Again, 354 divided by 130 equals 2.72 operators. It's very likely that the math will result in a way that requires a partial operator as it did in this example. The partial operator can be given additional non-work area related work to increase their productivity. Note, crew size is too small will often result in an overburdened process, MURI, that can lead to overtime and late deliveries. Crew size is too large can result in underutilized resources and reduced productivity. You may have heard lean thinking folks say U-shaped cell designs are better than linear layout cell designs. Let's look at the motion under both work cell designs. For processes where each operator works at a single workstation location, like the top figure, linear layout and U-shaped layouts require about the same amount of operator motion. On the other hand, for processes where operators work at multi-workstations, like the bottom figure, the U-shaped work cell provides less operator motion from the end of each cycle to the beginning of the next. Line balancing is an activity designed to ensure all operators working in the work area have workloads or cycle times equal to or slightly less than takt time. This is to prevent excessive queues and upstream work in process, and or excessive downstream wait times. Poorly balanced lines will drive up work area cycle time, which results in higher than necessary labor costs and lower than necessary productivity. The image on the right is an example of a line balancing tool. We use it to determine which process steps will be assigned each operator. The goal again is to have each operator fully utilized. And as mentioned when calculating the minimum crew size, it's very unlikely that the cycle times for each operator will be exactly equal to takt time. This is especially true for the last operator in the process. If any operator in the line is not fully loaded or utilized, additional non-work area related work can be given to increase their productivity. We always want to operate using the least amount of work in process inventory, or WIP. We do, however, need enough WIP inventory to produce to our customer's need. Standard work in process is a calculation that determines the minimum pieces of work in process needed to keep up with demand. It can be calculated by dividing the total cycle time by the takt time. As an example, if the total cycle time is 135 seconds and the takt time is 45 seconds, the process will need 3 pieces of work in process in order to keep up with demand. 135 divided by 45 is 3 pieces of WIP. Note, not enough standard work in process will often result in underutilized resources and reduced productivity. Too much standard work in process, or SWIP, can result in long lead times and excessive work in process inventory. Like SWIP, or standard work in process, minimum machine work in process is a calculation that determines the minimum number of units that need to be processed at the same time in order to keep up with demand. It can be calculated by dividing the total machine processing time by the takt time. As an example, if the total machine time is 450 seconds and the takt time is 45 seconds, the machine will need 10 pieces of work in process in order to keep up with demand. 450 divided by 45 equals 10 pieces of machine WIP. Note, too little machine work in process will not provide the throughput required for keeping up with demand. Too much machine work in process can result in excessive inventory costs. The main lean objective regarding changeovers is to reduce the changeover-related downtime. This is accomplished through following the 7 steps of SMED, or single method exchange of dies. First, we should separate the internal activities from the external activities. Internal activities are activities that cannot be performed until the process is shut down. External activities are activities that can be performed prior to shutting down the process. The second step is to standardize the external activities. This is so the activities performed prior to shutdown occur consistently and predictably every time. Step 3 is to explore opportunities for converting some of the remaining internal activities to external activities to reduce downtime. If so, we'll want to standardize those activities as well. Now, Step 4 and Step 5 are to reduce the cycle time of all changeover activities, starting with the internal activities since they generate downtime. And Step 6 and Step 7 are to automate or even eliminate activities when possible. OEE, or Overall Equipment Effectiveness, measures the equipment's availability, the equipment's performance, and the equipment's quality level. Each of these measures can be helpful independently. However, OEE is a holistic measure that includes or combines all 3 independent measures. OEE is calculated by multiplying the availability score by the performance score by the quality score. If the OEE is not acceptable, you should look at the 3 independent measures to determine where the equipment improvements are most needed. This is a common tool used to help establish the OEE score for any piece of equipment. As mentioned earlier, poka-yoke is a Japanese word that means mistake-proof. As we create or improve processes, we should always attempt to eliminate the potential for error. When doing so, the team should always try to identify mistake-proofing methods that are effective, inexpensive, and easy to implement. Now let's introduce pull production or pull systems. Single-piece flow, also known as one-piece flow or continuous flow, is the most efficient type of pull system. Single-piece flow works most effectively when processes are stable, have 0 defects, fast changeovers, and equal processing times, or a balanced line. When single-piece flow is not possible, a Kanban system can be implemented to provide a sufficiently sized buffer between upstream and downstream processes. As you observe this Kanban flow, watch what happens when a customer pulls finished goods from the warehouse. Now in this example, Kanban quantity for each area is 5 pieces. When 5 pieces are pulled from the warehouse, the upstream process is signaled to begin production in order to replenish the warehouse's Kanban. When the upstream process begins producing, this signals further upstream processes to also begin production, to keep downstream Kanbans replenished. A couple notes. First, if the finished material Kanban quantity feeding the next downstream process is too small, the downstream process may run out of work due to material shortages. Another note is if the finished material Kanban quantity feeding the next downstream process is too large, the inventory and floor space will all be increased. Now we'll step through a basic Kanban replenishment cycle. In this example, a customer places an order. This starts a sequence of events. First, shipping pulls the items the customer ordered from the finished goods supermarket and ships them to the customer. This creates an empty bin in the finished goods supermarket which reveals a Kanban card. The Kanban card is then moved to the Kanban board and placed in the to-do column. This card is a signal to production that there is work that needs done. The Kanban cards located at the top are the first Kanban cards received and will be the first Kanban cards to be processed. This process is called FIFO, or first in, first out. When production is ready to do the work, they pull the next Kanban card located in the to-do column and place it in the WIP, or work in process column. It's now that the work area begins producing the product. Once production is finished, the production workers place the Kanban card in the finished column. This is a signal to the materials resource, often called a water spider, to move the finished material back into its designated area in the supermarket, and this completes the Kanban replenishment cycle. A raw material Kanban system is similar to the finished goods Kanban system. Let's see how it works. In this example, a production worker pulls a Kanban of raw material. This starts a sequence of events. First, the material's Kanban card is moved to the Kanban board and placed in the to-do column. This card is a signal to materials that there is material that needs replenished. When a materials resource is ready to begin the replenishment process, they pull the next Kanban card located in the to-do column and place it in the WIP column. Now, as mentioned before, a buyer will then order raw materials that are provided by external customers. For raw materials produced internally, this is where internal production work begins. Once the material is produced and available for use, the card is placed in the finished column. This in turn signals the materials resource, again often called a water spider, to move the raw material to its designated area in the supermarket. This completes the raw material Kanban replenishment cycle. Work in process, or WIP, is the number of widgets or services currently being managed. Queue is a type of WIP. Widgets or services in queue are orders placed, however no value or work has been performed. It's often called backlog and represents how far behind production is. Process WIP is WIP that is having value currently added to it, but not yet complete. And finally, inventory is WIP that has been produced, however, the customer is not currently needing it. It's often called overproduction and represents how far ahead production is. Lead time is the total time required to fulfill an order. It's largely affected by each process step's cycle time, work in process, and work in queue. Lead time can either be observed or calculated. It can be observed by measuring the time it takes from the time an order is placed to the time an order is complete. Lead time can also be calculated by multiplying the number of items currently in queue and in WIP times the average completion time. Process efficiency is the percent of time value has been added to a product or service divided by the total lead time. Process efficiency is largely affected by each process step's cycle time, the work in process, and work in queue. Capacity is the maximum number of services or units that can be produced in a given period of time. Capacity is largely affected by cycle time, downtime, changeover time, and defect rate. This is a common tool used to help determine the capacity of any process. Inventory turns is the amount of times per year a particular part number's inventory quantities will be fully consumed and need replenished. Inventory cost is largely affected by supplier lead time, volume, and order quantity. Inventory turns is calculated by dividing the annual consumption rate by the average quantity on hand. Days of supply is the number of days remaining before a particular part number will be fully consumed and need replenished. Days of supply is largely affected by supplier lead time, volume, and order quantity. Days of supply is calculated by dividing the quantity on hand by the average daily consumption. Inventory cost is the average cost for a particular part number's inventory. Inventory cost is largely affected by supplier pricing, volume, and order quantity.
Congratulations on finishing this powerful training. If you're enrolled in our certification program, click on the Final Exam button when you're ready. Once we receive your exam results, our team will schedule a live workshop to combine hands-on experience with your newly acquired academic skill set. Once the exam and hands-on workshop are complete, our team will provide you with an internationally recognized certification. If you're not yet enrolled in our certification program and would like to be, click the I Want to Get Certified button.